Okay. Given 4 kilogram mass moving off in this direction with initial velocity, and that initial velocity ought to have an arrow over it. And so should the final velocity. We have an impulse J, 12 Newton seconds times I minus 9 Newton seconds times J. What's VF? Well, J equals change in momentum. So J also equals F net L to T. A lot of ways you can break this down. A lot of you use MV and stuff like that. Factor it out in M, etc. This camera will not, something's just a little bit off here, but we camera's cutting off things at the bottom of the screen. Now it's showing things below the bottom of the screen. I don't know if it's a camera or Zoom or what. Okay. Anyhow, back to this. We can directly calculate the change in the momentum. So one way to approach this is calculate the initial momentum, which is mass times the initial velocity, equals, and I'm not going to write it all out, just 4 kilograms. I'll write this much out. 4 kilograms times V naught, and that's going to give us 20 kilogram meters per second times I plus 8 kilogram meters per second times J. Can you read that? Let's make a better J here. Better arrow. So that your J your final momentum equals your initial momentum plus your impulse. Does that make sense? If J is your change in momentum, your change in momentum is your final momentum minus your initial, so that the final is the initial plus the change, right? That's all it's saying. J is your change in momentum. Your impulse is your change in momentum. So we can just write the result. That's going to be 20 kilogram meters per second I plus 8 kilogram meters per second times J plus 12 Newton seconds times I minus 9 Newton seconds times J. Well, a Newton second is what? It's a kilogram meter per second squared times a second. So let's just make a meter per second squared times a second is a kilogram meter per second, which is a unit of momentum. unit of mass times unit of velocity. So without explicitly doing the calculation here, because I did it over here, I'm going to just be able to add the 20 kilogram meter per second to the 12 Newton seconds, because a Newton second is a kilogram meter per second. I get 32 kilogram meter per second times I minus 1 kilogram meter per second times J. Now, VF is just your momentum divided by the mass, right? Okay, so what everybody pretty much tended to do was essentially divide this by the mass, and write it as m times VF minus V naught and everything, which is not incorrect. So I think most of you probably got a good result. If we think in terms of momentum, though, we don't have to get our hands dirty with velocities. Then if we want velocity, if we know the momentum and the mass, we can easily find it. Okay, so final velocities, final momentum divided by mass. Mass is 4 kilograms. If we divide kilogram meter per second by kilogram, we're going to get a meter per second. So we're safe in saying that when we do this division, everything is going to come out with kilogram meters per second if we just divide by 4. So we get 8 meters per second times I minus a fourth of a meter per second times the J vector. I want to be sure we use a lowercase j for the vectors so we don't confuse it with the uppercase J for impulse. Okay? Now, we can extend this a little bit. Let's just say that this impulse comes from an interaction with another mass. Probably not a collision, because I don't think the collision is going to work out this way, but maybe. Okay? Maybe that interaction could be a collision. Let's just assume there are two masses now. So again, we have our 4 kilograms. Two meters, this, okay. We have our impulse, and I'll use a different color for impulse. It's 12 Newton seconds minus 9 Newton seconds. So Newton seconds times I minus 9 Newton seconds times J. That Newton kind of blends into the 12 there, but you understand that that's just what we wrote over originally. Okay, now let's say that this impulse comes about from a collision with a 7 kilogram mass in this direction with a velocity of 4 meters per second times I minus 3 meters per second times J. So this thing is going to collide with this. Okay, so maybe these things are, this one's here, and then they collide. You're going to get a change of momentum due to the equal and opposite impulses. Okay. A little more. And over here. Okay. We're going to call this V10, and this is going to be mass M1. This is mass M2, 7 kilograms, and this is V20 equals this. We already calculated what V1F ought to be. Eight meters per second times I minus 1/4 of a meter per second times J. Okay, so what we're going to do is find V2F. Well, I meant to look up the convention for subscripts because I always get it confused. One of those things I haven't been able to keep track of for 60 years. Okay. I couldn't keep track of it when I was young and my brain actually worked. I still can't keep track of it. We all have these little oddities. I'm going to say this is the impulse exerted by mass 2 on mass 1. And again, I can have that back. Look at the way your book does it. So V2F the impulses are equal and opposite. So the impulse on this one is equal and opposite to the impulse on this one. Unfortunately, I don't have room, didn't leave myself room to draw that. But there it kind of is. It should be equal and opposite to this vector. Kind of cheated on the direction to make it a little longer. It's still not long enough. So I'm going to cheat over here, make this one a little shorter. I don't have my board stretcher, so I can't extend the board anymore. Okay. Okay, so painted myself into a corner here, but I'm going to call this J12 equals negative J2. And of course, that's going to be negative 12 Newton seconds times I plus 9 Newton seconds times J. So L to P 2 is the initial P2 plus J12. Okay. Yeah, but hang on. Got a question, so we'll pause for a second. Okay, now it's written a little poorly, but I've defined this to be J21, which I take to mean the impulse exerted by mass 2 on mass 1. Okay, so this is what I call J21, and I might have those subscripts backwards from the convention. Whatever I call it, the impulse on this one is equal and opposite to it. And it's not written very well. I'll close that J up a little bit. But that just says J12 equals negative J21. And I wrote that down here again. Now, why are the impulses equal and opposite? Because by Newton's third law, the forces are equal and opposite. And when you multiply equal and opposite forces by the same time interval, because they act during the same time interval while these things are in contact, you see that the impulses have to be equal and opposite. That's a basic principle. That's everything follows from that, everything in this chapter. Okay. So we can say that L to P2, which means the change in the momentum of the second mass, which is our newly introduced 7 kilogram mass, is equal to the initial momentum of that mass plus the impulse on that mass, the impulse being equal to the change in momentum. So that equals what? P2 naught is 7 kilograms multiplied by the velocity of this thing, which is 4 meters per second times I minus 3 meters per second times J. There's our P2 naught, our initial momentum of object 2. And then that's going to be plus the impulse, which is negative 12. And I'll still write this as Newton seconds. Newton seconds times I plus 9 Newton seconds times J vector. I should say the J unit vector because we got another J vector here. But we multiply this out, we get 28 kilogram meters per second times I minus 21 kilogram meters per second times the J unit vector. And now I'll make use of the fact we've already determined that the Newton second is the same as a kilogram meter per second. So it's negative 12 kilogram meter per second times I plus 9 kilogram meter per second times the J unit vector. Make sense? We're just adding the initial momentum to the impulse. So we get 28 kilogram meters per second and negative 12 kilogram meters per second times I, and then negative 21 kilogram meters per second and 9 kilogram meters per second times J. So we see this doesn't make a lot of sense. Uh, it's not negative 12. Yes, it is. Negative 12 plus 9. That's negative 12 minus 9. And that worked out over here. Oh, yeah. Okay, I get it. I never did show the final velocity. So the velocity of this one after collision is almost all horizontal. Okay. 8 meters per second I minus 1/4 meter per second times J. It's not kilogram meters per second, it's meters per second. So there's a final velocity of this mass. In the final velocity of this mass, well, I haven't figured out the final velocity of this mass. And there's a final momentum of this mass. I haven't left myself a lot of board space. Can I get that in there? I think I can. We're going to need more board space. Okay, so I've got my delta P2. Again, equals 16 kilogram meters per second I minus 12 kilogram meters per second times J. This means F is P2 naught plus delta P I'm sorry. I have a notation error when I wrote down here. This should not be delta P2. This should be P2F because J12 is J12. Now, let's not get too distracted by the subscripts. Again, all this is saying is you take your initial momentum and add your change in momentum, which is your impulse. And it gives you your final momentum. So when it wanted to write up here, not delta P2, it's P2F equals this. So V2F is P2F over mass M2, which means I'm going to divide this by the 7 kilogram mass. Okay. When I do that, I get okay, each term is going to be divided by 7 kilograms. So I'm going to have 16 over 7, and the kilogram will divide out. And that should be obvious. If not, give it some thought. And if you can't get it reconciled, ask me for more explanation. So this is approximately 2.3 meters per second times I minus 1.7 meters per second times J. So what's that look like? That looks like this, using this orange for my velocities. This thing is going to nearly maintain its direction because, of course, its initial direction is almost along the same line as the impulse. It's going to slow down a lot because this one speeds up. So we're going to end up with V2F approximately equal to 2.3 meters per second times the I vector minus 1.7 meters per second times the J vector. Does it make sense that this thing should collide with this? And if it collides with these equal and opposite impulses, it's going to slow down, but it's going to hit this one kind of angled in from behind and speed it up a little bit. Okay. So we can analyze the collision if we know what the impulse is. Now, one thing we've got to be careful of is we can get ridiculous results by assuming an impulse in a collision. What could be ridiculous is the final kinetic energy could be greater than the initial kinetic energy. So is this possible? The answer is yes. Provided the final kinetic energy is less than the initial kinetic energy, less than or equal. Okay. It turns out if it's equal, that's what we call an elastic collision. An elastic collision is one in which the kinetic energy and the momentum are both conserved. We know that the momentum is conserved in this collision, assuming the calculations are correct, because the impulse is the change in momentum. Okay, the impulse on this object is the change in its momentum, and the impulse on this object is the change in its momentum, and these impulses are equal and opposite. So the total change in momentum is 0. Let's calculate final and initial kinetic energy. The initial velocity here was 5 meters per second I plus 2 meters per second J. So this thing had kinetic energy of 4 kilogram mass times the speed of the object. There's your speed, which is straightforward Pythagorean theorem on your components, okay? So again, 4 kilograms times the square root of the quantity, 5 meters per second squared, plus the 2 meter per second quantity squared. That's all under the square root. Then we have plus 7 kilograms multiplied by the speed of this, which is 5 meters per second. That's just a 3, 4, 5 triangle. You can look at it. So I'm going to shortcut that so I don't have to write it all out. Should be clear if you got an I component of 4 and a J component of 3 or -3, you're going to get a hypotenuse of 5. So this is going to be approximately, that's 25, that makes 29. That's about 5.4 meters per second times 4 kilograms is going to be roughly 22 Let me correct this. There's your speed. And the kinetic energy is 1/2 mv squared. So you got to square this square root. And you're going to end up with 2 kilograms times 29 meters squared per second squared, which is 58 joules. And the 1/2 applies throughout here. That's going to be 25, and that's going to be 3.5. It's going to give you 87.5. If I'm doing my arithmetic correctly, that's going to be 145. So that's your initial kinetic energy. Abbreviating it a little bit. Your final velocity for one, you got 8 meters per second here and a 1/4 meter per second here. The quarter isn't going to amount to much. It's pretty much 8 meters per second. Say it's approximately equal to, because I'm ignoring that 1/16 of a meter squared per second squared there. And then you're going to have your 7 kilograms times your final velocity here. And that's going to come out around not too much different than 2. Well, okay, square 2.3, you get 5.29 and 1.87, 1.89, 5.2, 1.8 is like 7. Square root of 7 is like Okay, anyhow, that's going to be 64 times 2, so that's going to be about 128 joules, which is pretty close to your 145 joules, right? So we're getting up close to the threshold of the maximum kinetic energy you could possibly have in a collision uh, with these parameters. Okay. Square 7, going to get about 7. And you're going to get 175 joules. 177 joules. Okay, calculation aside, the point is that this is not possible. So I just made up an impulse here for the original problem, and I threw in a second object, gave it some velocity, and said, okay, the impulse is equal and opposite. Calculated the results of those assumptions and came out with too much kinetic energy. I came out with more kinetic energy than I started with. Now that's an important idea. As I say, if the final and initial kinetic energies are equal, you have what's called an elastic collision. For any collision, in the real world, until you get to the subatomic realm where quantum effects take over, your final kinetic energy is going to have to be less than your initial. You always lose some energy. If two things collide and make a sound, well, it takes energy to make a sound. So they lose some of their kinetic energy to sound. Okay. They also tend to heat up and they get compressed. So all kinds of things happen to make it impossible to do this. But you understand how we can use the impulse to conjecture a collision. What we want to do now is, if we have a collision, let's figure out what happens. Okay. So we analyzed a collision last time where we had two vehicles that collide and come to rest. Okay. Okay, I said they collide and come to rest in a reference frame that's moving in the right direction. If you're riding along with these things in the right direction, you'll see these things come together and then they're going to move off at the same speed you do, so they'll appear to be stationary in your frame of reference. That makes sense? Okay, well, you think about it a little bit. Just looking for board space here. So we could have a collision like where we have M1 moving with velocity V1 and M2 moving with some velocity V2. They could collide and stick together so that they have a common final velocity. if you calculate that common final velocity, you can find the change in momentum of each object. And you'll find that they're equal and opposite. The other is M1 and M2 with velocities V1 and V2. Align and conserve the kinetic energy. Now, that happens if M1 V1 plus M2 V2, the total momentum of these objects equals, before collision, equals the total momentum after. Now, what do I mean by U1 and U2? This is before. This is after. We have M1 moving at velocity U1, M2 moving at velocity U2. We understand two objects can come together like this and bounce off like this, right? They come together and bounce off. You can work out the equations, but it turns out that the kinetic energy is conserved if and only if the relative velocity of these things afterwards is equal and opposite to the relative velocity before. Now, what do I mean by relative velocity? Imagine these two vehicles, because you've been in vehicles approaching other vehicles. Okay? If you're driving at 50 miles an hour in this direction, somebody's driving at 30 miles an hour in this direction, what's your relative velocity? It's 80 miles an hour, right? It appears the same as it would. This is 50, and this is in the opposite direction at 30. They're approaching each other at 80 miles an hour. Okay? So as you see it, let's say you're in the first vehicle, then the relative velocity is going to be this minus this. Now, again, why minus? If you're moving 50 in this direction, somebody's moving 30 in this direction, and you think this is a positive direction, then you think they're doing negative 30, right? 50 plus negative 30 would be 20. Well, you're not approaching at 20 miles an hour. 50 minus negative 30 is 80, and you're approaching at 80 miles an hour. That's just common sense, but you got to reconcile the idea with common sense. So relative velocity, actually, I've got that backwards. It's V2 minus V1. Because the other thing is, if he's approaching at 30 miles an hour, you see him approaching in the negative direction, right? And the relative velocity of him with respect to you is negative 80 meters per second. And we'd say then that the relative velocity would be v2 minus v1. And I got here as seen from, I'll just call this M1, object one, okay? As seen from here, this guy's coming at you at 80 miles an hour. Your direction is positive, his is negative. Okay, now down here, the relative velocity is u2 minus u1, okay? Kicker is if, I'll even do it this way, KE is conserved if and only if first place, momentum is conserved, which I just wrote down here. I wrote a little sloppier up here. This says the same thing this does. And there's an adjustment here on the floor so we can get closer to the board. Okay. And I say relative velocity switches. That's not a very rigorous statement, but it's kind of the feeling that the relative velocity reverses, right? And probably ought to say reverses. I didn't have room to write it, but I better say it. So let's say reverses. That makes sense? Relative velocity before is then the negative of the relative velocity after. That conserves kinetic energy as long as momentum is conserved. This gives you two simultaneous equations you can solve. If you know M1 and V1 and M2 and V2, and you know that the collision is elastic, then the only thing you don't know is U1 and U2. And you've got two equations here with two unknowns. So it's easy to solve, assuming you can solve two equations with two unknowns. And most have been through linear algebra, but not everybody. So I'm going to have to ask you to look at the examples to see it, but very easily we could solve this equation for U1. And then whatever expression we get for U1, we plug in here. And now we solve for U1 in terms of V1 and V2, which we know, and U2, which we don't know. But the expression we put in here is only going to have U2 as an unknown, and then we're going to be able to easily solve for U2. Now this works in one dimension, it works in two dimensions. If it's in two dimensions, then you actually have two vector equations, even in three dimensions. But in two dimensions, you're actually going to have four equations. So I'll just say in two dimensions, you have M1 V1X plus M2 V2x equals M1 U1x plus M2 U2x. In other words, you just write out the equation for the x components. And you have then now I'm writing it here with the negative of the relative velocity. You see the equation, the formula in a book, they take it one step further. The negative of U2 minus U1 is U1 minus U2. So you could say, V2 minus V1 equals U1 minus U2. Okay. I prefer to write it with the negative to emphasize the fact that your relative velocity reverses. So if you have an elastic collision with that car approaching at 30 miles an hour, you're doing 50. Then after collision, before collision, he looks like he's coming at you at 80 miles an hour. After collision, it looks like he's going at 80 miles an hour away from you, which is much worse for you than an inelastic collision because your change in velocity is going to be less in the inelastic collision than it will in the elastic collision. In the inelastic collision, for example, two equal masses doing at equal speeds will come together and stand still. If the collision is elastic, they'll come together and bounce off like this. Now, I'm a little reluctant to demonstrate this because my neck is a little messed up, so I'm not going to do this very hard. If I lived through it the first time, I might do it a little harder the second time. But if I walk into this door, now normally I do this face first. My face is a little sensitive today, so I'm just going to hit the controller. Okay, so I walk into this door at this speed. Okay. That was an elastic collision. Okay. An elastic collision is one where I come in here and bounce off. In order to bounce off, I've got to exert a lot more force on the door. And if anything was going to injure my neck, that second one would have. That doesn't seem to hurt my neck. I don't think. Because of the neck, I'm not able to work out my shoulders very well. So I actually hit that door a little more bone than I was expecting, but it's not, and it wasn't hitting very hard, didn't hurt anything, as I can tell. Okay, you get the idea though. Okay, so me walking into the door like this is easier on me than bouncing off the door like this because my change in velocity is greater. I was approaching the door at 1 meter per second the first time, and my change in velocity was just 1 meter per second. Okay, change in speed. Change in velocity the second time had a magnitude of 2 meters per second. I bounced off at 1 meter per second. Okay. So anyhow, in this elastic collision, we have this, and then we have the same thing for the y. Um, and v2y minus v1y equals a negative of u2y minus u1y. And I don't remember what notation your text uses. V and U are common, so you could see that from some authors. Or you could maybe see V1 and V2, and then V1 prime and V2 prime. Use a prime for after collision, okay? whatever the notation is, the idea is that your relative velocity reverses. Relative velocity after is equal and opposite to the relative velocity before. So if you have information, you just put it into equations and solve. But you should understand where the equations come from. They all come from the impulse momentum theorem, which you derived successfully the first time I asked you to, okay? You just plug F net over m into the second equation of uniformly accelerated motion for the acceleration and solve for F delta t, okay? And you should remember that. Okay, I just said that going to give you a fairly light assignment this weekend because I know you're going to be focused on preparing for the test. I'm going to go through chapter 10 fairly quickly because chapter 10 is something I've been preparing you for all semester. It's angular velocity, angular acceleration, angular displacement, okay? Just angular kinematics. You have equations of motion that are exactly the same as your equations of motion, uniformly accelerated motion for linear. Instead of V, you use omega. Instead of A, you use alpha, angular acceleration. Instead of X, you use theta. Okay? And you just replace those things in the equations of uniformly accelerated motion, which you better be really used to. Okay? And I think you are. And you get perfectly good equations. The concepts of angular motion, well, we've done a lot of angular motion in the lab. The thing we've done the most of in the lab is that rotating quantity, rotating beam, okay? And what I'm really trying to get you to understand there is the kinetic energy of those magnets. And also how the potential energy of the descending mass goes into the kinetic energy of the magnets and the beam, okay? Now things get more complicated when we ask how much kinetic energy that beam has because different parts of the beam are moving at different speeds. And the magnets are moving at different speeds. If you put them closer to the center or given angular velocity, they have less speed. So they have less kinetic energy. So the parts of the beam that are close to the middle don't have a lot of kinetic energy. The parts that are out there at the end have a lot more kinetic energy. Something that's 10 times as far from the, a particle, the steel, at the end of the beam, that's 10 times as far as an equal particle, 10 times closer, 1 to 30 centimeters, 1 to 3 centimeters. This is going to have 10 times the velocity. How many times the kinetic energy? 100 times. Because kinetic energy goes to v squared, meaning that the stuff toward the center contributes very little to the kinetic energy. It's the stuff out to the ends that contribute most of the kinetic energy. So, when we're analyzing the lab, and I'm going to take it easy on lab analysis, so you have plenty of time to prepare them, and then I'll place them on you about mid next week. Okay. So that's kind of what we're going to do. We've got 5 chapters we still need to cover. And after next week, we've got about 4 weeks of class time left. 3 weeks before Thanksgiving and 1 week after. Going to take some time for review. So we got to keep moving. So I will give you some problems. Usually what I do is I try to select fairly straightforward problems between Monday and Wednesday, and then give you the harder ones over the weekend. Incidentally, if you haven't gotten it yet, I think I've emailed everybody some feedback on their homework. Okay, which for the most part, look, nobody looked like they were headed for disaster. Okay. But some people got, notes on several problems, where part of the problem was you didn't do it, even though you did everything else right. Maybe because you didn't have time, maybe because you didn't know how to do it. But I tried to give you some hints. So everybody should have gotten um, a fair amount of feedback. Some cases of feedback was, yeah, it's really good, but you left a few things off. Okay. Everything from that till, well, there are 12 problems and 7 of them, there was something wrong, even though in most cases there was something that started out right. Okay. We've got 5 minutes, which isn't time to do a whole lot. So I think I'll just save the rest of it for Monday and let you go 5 minutes early today.